Okay, Purple Room Podcast. Today, I have an intro now via Aiden. It is Absurdist, and today we're talking about cosmic microwave background things.
Cosmic microwave background radiation. Even I can barely say it.
It's a lot.
So,
I will be fidgeting with the fidgeting
your
is.
handwriting very well.
Uh,
Okay, so first of all, what is the cosmic microwave background radiation? Now I'm just going to say CMBR, and you'll understand what I mean.
Yes.
It's this. This is a picture of it. I can break down these words. Cosmic. It is in the cosmos. Cosmos is anywhere that is not the Earth. It is in the cosmos.
That's a good, actually really succinct definition of that.
It is. Sometimes it's defined as outside of the solar system. Sometimes it's defined as outside of the galaxy. But the point is not here.
Right. Elsewhere.
For any definition of here, it is not there. It is all of these stuff outside of there. And then microwave, it is in the wavelength of microwaves. Now, it is the same microwave that you use to heat your food.
Wicked cool.
The reason it's called a microwave that you use to heat your food is because it uses small waves, to heat your food. Now, light is both a wave and a particle. I'm disregarding the particles. We'll come back to that when we talk about how the CMBR works, because it is important. But for now, what we have to know is light is a wave. It goes like that. And this is a wavelength. From peak to peak that's called one wavelength. And a microwave is this wavelength. It's very small. There's a definition, but for now, it doesn't really matter how small it is. You have to know it's very small.
Smaller than the average wave.
It is extremely small. Now, that's not really relevant. So this is, it is not visible to the naked eye. Naked eye being, and your eye without any instruments. It is not visible. You can only see it in the microwave, in the microwave wavelength. And so you have to use a microdetector to see it. Now, the thing is, microdetectors are very sensitive, and
As that they will be detecting micro things. They must be.
yeah, and they also, you get a lot of noise, especially on Earth. A truck driving by could impact your experiments.
Oof.
Depending on how sensitive your instrument is. That's for a specific thing that's really extremely sensitive, measuring gravity. It doesn't matter. That's off topic. The point is, there's room for interference. Now,
So in order to see this, we need special instruments, and we need to understand that light is a wave. You've explained what a wavelength is, but what is the thing that we're talking about? What is the cosmic microwave background radiation?
Yeah. So it is not a physical object. You couldn't touch it. It is, well, first of all, you couldn't touch it because it's 14 billion years, light years away.
Fair.
But also,
You couldn't even aspire to touch it.
yes. It is a snapshot. Now, okay, first of all, it's a snapshot in time. Now, something you have to understand is light moves at a fixed speed. It is, I believe, 3 million kilometers per second, if I remember correctly.
Something like that.
It's a large number. I do not remember the exact one off the top of my head. It's 3 with a lot of zeros following it, kilometers per second. I'm getting hot. So the thing with that is when you look out into space, because light moves at a finite speed, you're looking back in time. Technically, this happens on a much shorter scale as well. I look at JJ, I see JJ as far back in time as the speed of light. That's time that light takes to reach JJ.
That's
to me.
so cool.
But on this scale, it's basically instant. It is functionally, there's a thing in physics that you call functionally something. If something is so close of a measurement that it's basically the same.
JJ is functionally human.
JJ is functionally, I see JJ functionally instantly.
Yeah,
So,
that's helpful.
yeah. So, but the sun, if you ever heard, the sun is 8 minutes away, the sun is 8 light minutes away, meaning light takes 8 minutes to get from the sun to us.
So a light year would be how fast light travels in a year.
Yes, I
Got
should explain that. But yes, it is a unit of distance, not of time, which is kind of confusing because it's a light year. But it is the amount of space the amount of area that light can, the distance that light can cover in 1 year. So take whatever the speed of light is, and then put it in years, not seconds, and then that's the number you have.
Got it.
So
that's why we can't touch or think about this as a physical object. But what it
Yes.
is like a snapshot in time.
yeah. So it's a snapshot in time of one specific moment. It is the moment right before the universe became transparent.
Which is just wild to think about. Like the universe is transparent, and B, that we can see it.
Yeah. So the universe is transparent, meaning there is nothing physical about, there's nothing inherent to the universe that stops me from seeing other things. I can see the sun because the universe is transparent.
Ah.
I can see it. The universe being transparent is talking about the near vacuum of space.
So if it was opaque, we wouldn't be able to see things like the sun or other planets or whatever, because whatever was making it opaque would be in the way.
Exactly. Now, what was making it opaque is heat.
Ah, okay.
There is a fundamental misunderstanding of heat that a lot of people who are not physics nerds have, because for our purposes, heat, for like human day-to-day purposes, it's fine to just think of heat as things being hot, and you don't have to know why. But in terms of physics, heat is the movement of particles. So
Makes sense.
when something is hot, particles are moving around. They're like bumping into each other.
The hotter it is, the faster they go.
Exactly.
Okay.
And frozen things, the reason that frozen things are so hard is because when things freeze, they get into a rigid structure. And so if you look at water particles, they're just kind of dotted all around, and they flow and they interact. If you look at ice particles, at ice on like very close up, you see this, a grid pattern.
Ah.
And you can't move it. The bonds are really strong. So
we're talking about thermodynamics and why heat makes the universe opaque.
So light. Now we have to think about light as a particle. Now we thought about light as a wave earlier. Now it's a particle. It is both. It's kind of confusing to think about it like that. So a lot of people think about it as light and a particle at two separate times, which I know makes sense. But the particle of light is called a photon. Now photons, like with any particles, bounce off of things. That's how you see. A photon bounces off whatever object you're trying to see and into your eye. And then your eye detects it and sends that information to your brain, and you process it, and that's what seeing is. I can see JJ because light is bouncing from the sun onto JJ into my eyes.
Heck yeah, it is.
That's why it's hard to see when it's dark, because less photons are bouncing around.
Oh, okay. Like, I feel like that was something I could glean, but like it was never explicitly stated, and therefore, like, okay.
So it's never explicitly stated, but it's like the most fundamental, like, you can't see when it's dark.
Correct.
And so, like, that's the most, like, in your brain making sense way of thinking about light as a particle. This is also why, like, night vision is a thing. When your pupils dilate when it's dark in order to see more. That's because it's trying to take in more. When pupils dilate, it can take in more light. And so the very few photons that are scattered around bouncing off of things are more likely to get into the surface area, which is occupied by your eye. Now think about, if you remember, there's a thing called flux. It's basically the amount of energy going through a certain area. It's energy per unit area. So if you have a sheet of metal, like a box, like a square. In that square, the square has an area, and in that area there's a certain amount of energy going through it. This is really useful for talking about things like brightness. And so your eye has a certain flux. When your pupils dilate, the area gets bigger, so you can take in more light.
And this pertains to light as a particle because we're talking about thermodynamics in order to understand CMBR.
So the reason this is all relevant is because photons have to are able to bounce off of things. Now, if you remember, heat is dense and fast-moving particles. I forgot dense, but dense and fast-moving particles. And so when the universe, so Big Bang happened, boom,
Yep,
there's
vacuum.
there's an area which is very dense and very, very hot. So all the particles that make up the universe are jiggling around, they're very dense, they're very hot, they're moving really quickly, so photons can't get through.
Which means we cannot see through it.
Which means you cannot see through it. You just see a blank screen, basically a static on your screen, because there's no way for the photons to travel through the heat to get to your eye. So the CMBR, this is a picture of what the universe looked like the moment before it cooled down enough that the particles stopped moving so we could see through it.
That's insane to think about.
Yeah.
And also, like, so is it everywhere if it's background radiation? That makes me think, like, it's hard to think about a snapshot and also something that is ubiquitous.
Yep, it is everywhere. It is a 360-degree view. It is everywhere. This is just a common representation of it. If you wrap this around, it would become a sphere. It's just like you see like world maps that look like this. That's because it's trying to represent a sphere, and you fundamentally cannot accurately represent a sphere on a two-dimensional object.
It's true.
So I actually saw a globe once. I saw a collection of 3 globes. There was one that was the Earth, there was one that was constellations, and there was one that was the cosmic wave background radiation.
Oh,
and
that's
it was
cool.
cool as hell. But yeah, this is what it looks like. This is a fundamentally flawed representation because it is two-dimensional, but it's good enough for our purposes.
So let's see. So we have the universe, speed of light, and looking backwards, and the cooling. That's probably where we're at.
So the cooling is basically saying if you think about heat as objects moving around, cooling down is when those objects slow down. This is part of what I'm way glossing over a bajillion amounts of thermodynamics, which are cool.
And that is A-okay.
I'm just saying, like, this is a way simplification. Do not use this to do physics. Because it will be fundamentally
You've
flawed.
been warned.
Yeah. Do not do what I am doing in order to try to solve a problem. It's not going to work. That being said, one of the reasons that things cool down is because when things are moving really quickly, if they have, for example, some sort of resistance, they'll stop moving. So things cooling down. I'm glossing over that, but things cooling down is things slowing down. It's the fundamental particles that make something up slowing down. And so when the particles slow down, you can bounce a particle through them. Think about bouncing a ball through a moving maze.
Okay.
You can't really do it. It'll bounce off of all the walls and it won't get where you want it to go. It's just not going to work very well. But when those walls line up and kind of slow down, you can do it. You can do it 9 times out of 10. And then when they stop moving, you can just do it every time.
Okay.
That's kind of what happened to the universe. Right now, the universe has cooled down so much that it's a near vacuum, so there's nothing to bounce the ball off of.
Right.
It's kind of like if the walls of the maze were really, really close together and then just kind of spread out. And
That's
now
really
they're
helpful.
so far apart, they barely matter anymore.
That's
why,
really, really helpful, actually.
Nice. That's why people call it a vacuum. It's technically a near vacuum because there are particles floating out there, but it's so close. It's so close it is functionally a vacuum.
Okay. And that is important to know about this because it explains why we can see it and why it appears the way it appears now.
Yes.
So,
and the other thing is because this is also, if you ever heard someone talk about the observable universe, this is what they're talking about. Everything within the CMBR is the observable universe. And because light moves at a certain speed, the CMBR is moving further away.
I thought it was everywhere.
Yes.
But everything in the universe
is
is
expanding.
moving.
The universe is expanding. And this is the edge of the observable universe. So that is also expanding because light travels from it to us. And the longer time it has to travel, the further it can travel. So the further away it looks.
Ooh. So how do we know this exists? Because I want to know about that.
It's the funniest story. So the first time I heard this, I thought it was a joke. It's not a joke. This is actually what happened. A group of scientists owned a microwave detector. Now, these microwave detectors, they're pretty cool looking. They basically are a little building with a bunch of computers in it, attached, this is too far down, attached to a giant dome, a giant like cone that looks up to the sky. This is a horrible drawing, but it doesn't really matter. The point is, this is what a detector looks like.
Okay.
And it bends light. It doesn't really matter how it works. The point is, it detects microwaves. It's very complicated. I don't fully understand it myself. It basically bends all of the microwaves into a smaller area so it can detect them easier. It's a thing.
Cool. Okay.
So,
I mean, I believe it.
they were trying to detect microwaves. Now, I don't actually remember off the top of my head why they were doing that in the first place, but they were. And they figured out that they could detect microwaves, but there's like a buzz in the background. If you have like an old speaker system, sometimes there's a high-pitched whine in the background. It's kind of like that. It's just there constantly. And they couldn't figure out what it was. So they pointed at a different part of the sky, and they couldn't figure out what it was. And they pointed it to a third part of the sky, and it was still there. And they were like, okay, well, this is a big cone-shaped thing up to the sky. There are pigeons nesting in it, so there's probably pigeon poop everywhere. So a guy with a scrape goes in and scrapes all the pigeon poop out. And they're like, okay, it's fixed. It was not fixed. It was still there.
So they thought the cosmic microwave background thing was pigeon poop.
And they also thought
That's
that it was
amazing.
they also thought that it was just like a miscalculation. They were thinking like, maybe we built this very slightly wrong.
Awesome.
And it's so sensitive that if it's built a micrometer off, it's broken.
Well, that tracks. I mean, it's
Yeah.
sensitive, made to detect tiny things. Okay.
Yeah. So then they went to other like people who were trying to detect microwaves, and they also found this. And they were like, we don't know what it is either. And so what's more likely, that there's something out there emitting microwaves, or that every single thing on Earth is just broken? It's probably, that's a wrong question to ask because we're really bad at making things as humans. But
Yeah, we are.
we think that we thought that it was something out there in the universe that was causing this. So, what is it? A bunch of cosmologists got together, looked at the data, and they mapped out the data based on temperature. Now, temperature, they figured out like the frequency of the waves, like it doesn't really matter how, but they mapped out temperature. And they created this map. Now if you see on the bottom here, there's a little
Scaly boy.
Scaly boy. And it's
It's a scientific term, y'all.
yes, it's labeled as temperature. Now this is temperature which is deviating from the standard, meaning that the temperatures that you see, if it's colder than the average temperature, it's bluer. If it's hotter than the average temperature, it's redder. And if it's about the average temperature, it's bright green. And so they noticed that, and they noticed that there's slight variation, so it can't be a malfunction because there are variations. It is a variated thing, and it's standardized across every single detector. Every detector found the exact same thing.
Ooh.
So it can't be a malfunction unless everything's malfunctioning the exact same way in a way that makes it so when you look at different parts of the sky, it looks different. Which it doesn't happen. You can't malfunction in a slightly different way depending on where the telescope is pointing. That just doesn't work.
Fair.
So
So it's more process of elimination than anything else for this.
That's kind of how a lot of astronomy works. You come up with theories and you discard them until you find one that fits the map.
Okay.
It's just a fundamental way that physics works. So with this, they found out this is what it was, and then a bunch of cosmologists got together. Cosmologists are people who study the creation of the universe and all the theoretical stuff. Big Bang was cosmologists. They theorize about the universe. And these are things that the reason I don't really want to be a cosmologist is because they think about what is possible and they don't have any concrete way to prove it. You can't go back, you can't build a time machine and say, okay, the Big Bang did actually happen. I went back with the time machine and saw it with my own eyes.
Right.
So
Makes sense.
it's just math. And then maybe in 10 years, we're going to do another experiment and find that there's some math that just makes it so the Big Bang isn't real. And then we'll look back on ourselves from 10 years ago and be like, ah ha ha, those idiots, they thought the Big Bang was real.
It's like the equivalent of like looking at your mom's high school photos in the photo book and being like, what a shitty haircut you had.
Giant, that's off topic. Anyway, but yes, definitely. It's interesting. This is part of what I love and part of what I hate about astrophysics in general. You make theories, you fit them to the math as best as you can, and then new math comes along and contradicts everything.
That must be like a little bit frustrating.
It is a little bit, but it's also really cool because it's a field that's always evolving. There's always something to do. There's always something to figure out. Special relativity came around. Quantum mechanics came around. well, the way quantum mechanics works is one person, Einstein, I think, I don't remember off the top of my head, I think it was Einstein, looked at the math and said, okay, there's one number that is not coming out. Like, there's not one number that's not coming out right, one little equation that's not working, I need one more variable that's not adding, it's not adding up. What's going on? He did a bunch of math. He thought, this is an easy fix. This is an easy fix. This is going to be, it's one variable. It's not going to take me any time. It's going to be fine. It's like 50 years later, we still don't understand it. Quantum mechanics is so complicated. It was created as a fix to a problem that was microscopic, quantum, and then it snowballed into this giant thing that physics majors everywhere hate. Is the bane of physics majors and just physics people in general. Anyway,
which probably leads us to like so we found the cosmic microwave background radiation, but CMBR.
Yeah.
It was not pigeon poop. We know what it is now, but like, what does that mean for the field of whatever we're doing?
Cosmology.
What does that mean for the science?
So a few things. Now, it's one of the biggest pieces of evidence for the Big Bang. And like, not one of the biggest, but like, it is evidence for the Big Bang. It is like, it's important. I can't articulate exactly why, but it is important. And one of the biggest things is we need to know what the universe looked like at the beginning, like towards the beginning of the universe's creation, to understand how it got to where it is now and what happened. So if you look at this, it is not uniform. Pick it up again. It is not uniform. You can see like there's blue splotches, there's red splotches. It is different. And if the universe was like uniform, if it was, picture soups. This is a soup, this is a stew. It has little chunks of vegetables and like croutons maybe. It has chunks.
Hungry.
I'm really hungry too. It's not like, think of like creamed soup.
Okay, like a bisque.
Uniform. It's just uniform.
Okay.
There's no variation. It's like blended up, no variation.
Yep. We got bisque, then we got like the sort of chicken soup. There's stuff there, but it's not it's stuff in a broth. And then stew, where it's like, yes, thick deliciousness with chunks of thicker deliciousness.
Exactly.
So we're at the thicker deliciousness.
We're at the stew part. there's stew, so here's the thing. There was stew, and the stew, this is where the soup analogy falls apart. The stew turned into like matzo ball soup, where you have like chunks of matzo balls, and then you have noodles and a few vegetables sprinkled in, but it's suspended in a broth. That analogy will make more sense in a second. But it has not and will never be a soup. Like a soup.
Right.
Smooth.
Like a bisque.
No variation. I don't know what a bisque is.
A bisque is the exact type of soup you're saying. Like if I had tomato bisque, it's just uniform.
Yeah, so it's a bisque. It's never gonna be and never has been a bisque, and we know that it never has been because of the CMBR.
That's cool. Yeah. So we know not just the state of the universe as it is, but the state as it was.
Exactly. And that's true of any astrophysics, because if you remember, the speed of light is constant. It never changes. It is a certain speed. So we're looking back in time, so we always know what the universe has been like.
That's cool.
Up until 14 billion years ago, when CMBR is. It feels weird to say is for something that happened 14 billion years ago.
Right.
But it is still, like, we can observe it, so it feels weird to say was.
Right. It wasn't was. It is.
This whole thing is weird. Like, English kind of falls apart when you get to this kind of funky, fucky-wucky math stuff.
Yeah.
And so this is why technical language was invented. Like specialized language.
Jargon has a purpose.
It really does. So, this is not uniform. Now, something about gravity is gravity takes a centralized point and pulls everything towards it.
Yep.
The center of the Earth pulls everything in. That's why people in Antarctica don't fall off the bottom of the Earth. It's because gravity. It pulls you up. Now, or in, I guess. It's less down. So we think of the gravity as going down. It does not. It goes in.
That makes sense.
We just experience it as down because we live on the surface of the Earth.
It's true.
Which is a globe. So gravity pulls everything in. Now, if you have a disk, you have nothing for gravity to do. Gravity doesn't exist if it's completely uniform because there is no center of gravity. Gravity requires a denser area to pull things towards. This is why the moon has less gravity than the Earth because it is smaller. And so it pulls things in weaker because it has less stuff.
Yeah.
Gravity is relational. It has relation to how much stuff there is. In weird ways, it doesn't really matter. Gravity is a whole different thing. The point is, gravity can't act on something that isn't there. If it is completely uniform, no gravity.
So we know that the universe was never uniform based
Yes.
on this.
Exactly. And based off of this, we know that we also knew that it couldn't be uniform because there is stuff now. So it couldn't have been uniform because gravity wouldn't have worked on a uniform thing.
Yeah.
So we knew it, but it's nice to confirm. And it's an interesting visualization because if you look at the little splotches, those are higher gravity areas which pulled other things in, which then turned into things like stars and planets.
So freaking awesome.
Yeah, stars are literally gas compressed by gravity really densely in order to kickstart fusion, which turned it into a giant ball of gas that we think of.
Which then suck other things in and star stuff.
Star stuff, it's cool.
It's really cool.
But the point is, if you don't have the matzo balls you can deal around, you're not going to do it. So it used to be a stew. Things kind of fell in, like got gravitied into more like clumpiness. It was uniform clumpiness. It was like fairly distributed clumpiness.
Mm-hmm.
Then gravity happened and it got more clumpiness. And now we have today a matzo ball soup where you have the star and the planet and very nothing in between.
So were there theories like kicking about at the time that this disproved entirely by finding it?
A lot of like cosmological, like Big Bang type theories, like how the universe started, a lot of those were disproved. Because there was a lot kicking around about like, there was a giant ball of planets, and then like a giant ball of stars, and then the stars themselves got shoved out.
Okay, like bowling.
Like I think of an 8-ball. If you ever played like 8-ball pool, you have the triangle of balls in the center, and then you hit them and they scatter.
Really good analogy.
And so that was a thought that what had happened, but this says it didn't. This says there was a giant uniform, like not uniform, but like a giant soup, a giant stew, and then stars formed.
Yeah, which like, it's interesting to think that people ever thought differently because like I don't even have like the cognitive scaffolding to think about it differently just because this is so saturated now in culture.
The Big Bang Theory is so like it's so immersed in popular culture, you don't even think of it as a theory. Like if you ask people what happened to what started the universe, they're not gonna say there is a theory called the Big Bang. They're gonna say the Big Bang happened.
Yeah.
And like as definitive. At this point, it is so well proven that it's very unlikely that it'll ever be disproven. This is something that happens in cosmology and in science in general, where a theory gets so widely adopted and so thoroughly proven that it becomes almost fact.
Like the theory of evolution.
Theory of evolution. We technically don't know, but it is so likely that in the general media, we just say it is a fact.
And it is a fact, correct me if I'm wrong, it is almost a fact because we discovered cosmic microwave background radiation.
The Big Bang, you mean?
The Big Bang, yes. That.
So partially, yes. There's a bunch of other factors. Like the theory of the Big Bang is super complicated, and it's not just like one or two things that people were like, that happened and that happened, therefore this third thing happened. It's like that happened and I think that happened, but that also means this happened and that means that happened. So if all of these things combined, and then we do a buttload of math, then we get to the model which looks the most like the Big Bang.
Yeah. So to recap,
Yes.
wavelengths, thermodynamics, particles and waves at the same time, heat, opacity, Big Bang, soup.
Pretty much. That's pretty much. Yeah, that's pretty much it.
In there. Like, and what is the coolest thing about the CMBR? I'm not even going to try to say it anymore.
Oh, that's hard. I think one of the coolest things is how it snowballed into so many discoveries.
Ooh!
Because if we know that the CMBR exists, then that's evidence for the Big Bang. If we know the Big Bang exists, we can do other theory. Like, the Big Bang is not just a theory, it's a foundation to do more science.
Okay.
This is another thing that I love about a lot of astronomy, is you make discoveries and then you build on those. Without the Big Bang, we wouldn't, without the theory of the CMBR and the Big Bang, we wouldn't know, like, all about nursery nebulae and, like, all of these other things that we would not have been able to figure out, or it would have taken us much longer to figure out if we didn't have the foundation of the CMBR and the Big Bang.
That's so cool.
I think that's my favorite thing.
So
honestly.
today on the Purple Room your topic has made my words not work by trying to say cosmic microwave radiation background
Yeah.
the whole time. So Purple Room podcast today, like the reason we have the science we have is this theory.
And no
This
one knows
fact.
about it, which is
And-
insane.
But now they do, because
Yeah.
like you get to be like, hey, actually let me lecture you about this.
Mm-hmm.
Yeah.